This is the biggest, hottest, and most explosive video on fireworks ever, covering everything from the invention of gunpowder to how fire can burn underwater, how fireworks are made, the colors, shapes, fuses, to how they're launched. We'll even see what it's like to fly through fireworks. Mr. Beast has got nothing on this. This video was sponsored by KiwiCo. More about them at the end of the show.
I cannot believe the precision with that huge camera on there. Gene is going to try to fly the FPV drone actually like through the fireworks as they explode. You ready, Gene?
I think so.
Gene makes a channel called Potato Jet, and he does tech reviews, but also lots of very filmic stuff.
A lot of
drone work.
Lately, a lot of drone stuff.
Okay.
A lot of fast drone stuff.
FPV drones.
Like this one.
Are you willing to fly this into a firework as it's exploding?
That's the goal. If I can catch it, that's the hope. But we set it up just for that, so I think we can get it.
The first recorded instance of something like a firework occurred in China over 2,000 years ago, where people would get a piece of bamboo with the ends closed and they would throw it in a fire. So as it heated up, everything inside would get hot and expand and eventually burst, creating this bang, which they thought scared off evil spirits. Then they developed black powder, and they put black powder inside the bamboo to make an even bigger bang. That was much more impressive. I want to test out the earliest known recipe for gunpowder. It involves 3 ingredients that you can find out in nature. The first is potassium nitrate, which actually comes from bat and bird guano. Once they poop in the cave and it dissolves in water, you get these white crystals coming out. The second ingredient is sulfur, these yellow crystals you can just find on the side of hills or around thermal vents. And the third ingredient is honey. That is the major fuel for the gunpowder. Now I'm gonna mix this all up. Looks like it could be frosting. So yummy. Earliest known recipe for gunpowder. What people observed was when they heated up this mixture, it would spontaneously catch fire. I have no idea how big of a thing this is gonna be. This is only about 1 gram of it, so I don't think it's gonna be huge. As we heat up that very primitive gunpowder, we should see it burst into flames. It's gotta be close. Here we go, here we go. Yes! We have made gunpowder. Now that took a long time before we saw the fire, so why is that? Well, honey contains a lot of water, and that's gonna slow down the rate at which this is gonna start to combust. People figured out that a better fuel was charcoal.
There are 3 things you need to make fire: fuel, oxygen, and heat. In most fires, the oxygen comes from the air, but in gunpowder, the oxygen is supplied by one of the solid ingredients.
The potassium nitrate gives you the oxygen, it's KNO3, so there's a lot of oxygen in here. And then the charcoal provides the fuel, that carbon.
Charcoal is basically just carbon, but it works better than other forms of carbon like graphite because it contains these microscopic pores. And that enables the reactants to mix much better. They can actually get inside those pores. So if you mix potassium nitrate with the fuel, charcoal, and add heat from a lighter, you should have all the ingredients you need to make fire.
So the question is, will this burn? It seems like little bits of it are catching on fire and just like sparking up from there.
But the trouble with this reaction is that it has a high activation energy, so it needs a lot of heat to get going.
Whoa, there it goes. That is cool. I can see little balls of molten stuff in the crucible there. That is awesome. So we do have oxygen and fuel and we can get that reaction, but it's just not a very explosive reaction.
This is where the sulfur comes in. Sulfur starts reacting with the other ingredients at lower temperatures, and those reactions give off heat.
The sulfur is going to act like kindling. It's going to create that initial bit of heat that the potassium nitrate needs to really break it open, and then, you know, everything can react. So that's what I want to do. I want to try to mix sulfur, potassium nitrate, and charcoal, which is like your quintessential recipe for gunpowder. And the amounts that you need of this have been pretty stable for like 800 years, which is about 75% potassium nitrate, 10% sulfur, and 15% charcoal. Those are the right mixtures so that you have just the right number of each type of atom to fully react and release the most energy possible.
So I want to test how long it takes for fire to burn down about 1 meter of this homemade gunpowder.
Let's let her rip. There it goes. Hey! It's going so slow. Come on, you can do it. Go, 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 go. Wow, it made it to the end. You know what I think the problem is? The granules of charcoal that I've got and these grains of potassium nitrate, even the sulfur, they're all a bit big. So to actually get that reaction to happen fast, it's not really working. So what I want to do is compare that to store-bought gunpowder from, you know, a factory that's actually ground up all those particles to be really tiny, so all the reagents are really close together. Oh my! That is impressive! Yes! That is gunpowder. That makes mine look so amateur.
The chemical reaction that occurs in the combustion of gunpowder is complicated, to say the least. But a number of the products formed are solids, and that's why burning gunpowder creates a lot of smoke.
The neighbors have got to be looking at this and being like, what the... The thing about gunpowder is, if you burn it when it's just exposed to the air, it doesn't really explode, and I think of gunpowder as explosive. But in order to see that, what you have to do is confine it. Because when you confine gunpowder, you increase the concentration of all the reagents. They don't just blow away from each other when they catch fire, so they're forced into closer proximity, so they react more. Plus, you trap more of the heat. So the reagents get moving faster, they have more energy, and so they can react more readily.
So I put 10 grams of gunpowder in a cardboard tube and taped it shut. Okay, that's better, but it wasn't as big of a bang as I was hoping for.
Well, it was a bit more of a pop than a bang. Maybe we need a tighter vessel, I think.
So I'm gonna use some fiber reinforced tape to strengthen the container, and then we should get a bigger bang.
It went right past me.
It's more of a bang, that's a bit more like it. Here I have 20 grams of black powder. So I guess the question is, with twice the black powder, do we get twice the bang? Here we go. Everyone get back.
This is essentially what a firework is. I mean, fireworks consist of a shell with a lot of gunpowder inside.
So this is an inert shell. It's colorized so that you can see the individual pieces better. A real shell, everything in here would be black because it would be primed or covered with black powder.
Actually, a note about terminology. For a long time, the terms gunpowder and black powder were used interchangeably. But these days, the formula for gunpowder has changed to make it smokeless. So what's used in fireworks is called, at least in the US, black powder, to distinguish it from modern smokeless gunpowder. Just know that in this video, we'll use both terms to mean basically the same thing.
The shell itself is made out of cardboard and what looks like and is a form of paper mache with craft paper and a glue. And you go around and around once you put the two shell halves together.
Is that like the standard size you'd see when you go out?
So on a 4th of July display, you'll see anything from 2.5 inch up to 5 inch typically. In most cases, 6 inch and above are reserved for locations that you have a huge property, you're out in some desert shoot site, or on a barge somewhere, but they can go even bigger than this, up to 12 inch, 16, and even larger in very special occasions. This is the hemisphere for a 16 inch diameter aerial shell.
That is a huge firework.
The biggest aerial firework ever was 1.44 meters wide, and it weighed about the same as a car. To launch a firework into the air, the way it's done is with more black powder.
In a typical shell, you're gonna have a baggie of black powder that's underneath the shell, and that acts to fire the shell out of the mortar to the 800 feet in the air, which is what this 8-inch shell would go to. Shells as large as, say, a 16-inch, those can use literally pounds of black powder underneath them.
To ensure the shell goes straight up, it's placed in a big plastic tube called a mortar.
A pyrotechnician gets 2 bangs for every one the audience does. You get a bang when the mortar fires, and then a bang when the shell explodes. And it's literally like a cannon shooting a cannonball in the air. So the audience doesn't get to hear, see, or feel that, but the pyro crew does.
Does everything burn up before it reaches the ground?
The internal contents, yes, so all the stars, the burst, all of that stuff. The casing will come down in pieces. That's why we have a fallout zone, what we call it, or the exclusion zone, where only the crew is allowed with all their PPEs, because you do get debris that comes down. It literally sounds like rain at the end from all of the debris from the finale shells going off all at once.
How often do they malfunction?
It's rare, but it does happen. You'll have a wooden rack with a few HDPE, high-density polyethylene mortars in it, and that particular material is meant to expand and split from the energy of a malfunctioning shell versus explode and throw shrapnel everywhere.
We actually experienced an incident like this with the biggest shell we had set to launch.
Okay, in 3, 2, 1. Uh-oh. That one did not look like it, That's what happens when a firework doesn't lift.
But because we follow all the rules and regulations at a professional display, it's usually the crowd going, whoa, and the crew going, whoa.
Oh my God!
And then the show goes on. It's typically what happens after a few safety checks when something like that goes on.
Thankfully, everyone was safe because we could trigger the fireworks remotely from outside the blast radius. But igniting explosives safely has long been a challenge.
In the mining industry, their delay method back then was to literally sprinkle out a trail of black powder through the mine to give them a delay to the dynamite.
The simplest fuse just consists of cotton string that's been soaked in black powder and then allowed to dry out. This is known as black match. It burns well, but pretty slowly.
That alone would burn 2 to 3 seconds an inch. But once you encase it in craft paper, that's literally all this is, you change that burn rate from a couple seconds an inch to anywhere from 30 to 100 feet a second.
This has the same effect as containing the black powder. It traps in the heat and reagents, so the reaction goes much faster.
This is actually how we shoot our finale so fast. We're not actually pushing buttons that quickly.
This type of fuse is appropriately known as quick match. Now, before I'd ever seen quick match in action, it was suggested that I try to race the signal down the fuse.
What I'm gonna do is light this little piece of black match right here, and then I'm gonna try to race the signal to the other end.
But still, I was not prepared for what came next.
Ah! Jesus! What the heck was that? You are kidding me! You didn't tell me it was gonna do that?
The force of the combustion products causes the quick match to whip around wildly.
It's crazy how much just containing the reagents and containing the heat from the reaction accelerates it.
It certainly burns much faster than the black match without the paper.
Man, every time that gets me.
One problem with these basic fuses is they aren't waterproof. Even though they contain the fuel and the oxidizer, so they don't need the oxygen in the air to burn, they do need heat. And water is just too good at conducting the heat away from the fuse, so it snuffs out the reaction.
And it fizzles out.
The same problem occurs with road flares. I thought since the flame comes out with such high pressure, it might be able to stay lit underwater.
3, 2, 1.
And it did for a little while, but eventually the water got in there and stole the heat.
So I think that the water is putting it out by pulling the heat away from it, so it doesn't have enough energy to keep burning.
We bring it out.
Come on, come on. Ah! Wait. Hey! Hey! And
There are special flares made for underwater applications, but even those have similar problems. You can see the gaseous combustion products being released here and bubbling to the surface, and while this flare lasted longer, the water still eventually put it out.
come on, why did that go out?
But it is possible to make a waterproof fuse.
So this is your traditional visco fuse. You're gonna see this in a lot of your consumer fireworks.
Very big fireworks store. I feel like we have to get this. Spins and emits fire? I'm excited about this one. Here we go. In 3, 2, 1.
It's really got a powder core with a fiber wrap to it. And it's typically lacquer coated, so these fuses are typically waterproof.
Whoa! Wow! That was impressive.
Fuses are not only used to light fireworks, they are a core component inside a firework.
So that quick match flashes really quick down into the black powder lift. That ignites, and while it's pushing the shell out of the mortar, it lights the time fuse. So this is what would actually be in the shell to give you the time delay from the time the lift charge fires to the time the shell hits apogee and explodes in the sky. You know, it's about a 1/4 inch in diameter and is really a black powder core rigid fuse compared to the more flimsy visco type.
It's really important that the time delay fuse keeps the combustion contained inside it, so the firework only explodes when you want it to, at the very peak of its trajectory. So we tested it underwater.
But you think it's waterproof?
Should be.
All right. It's taking its time. There we go. That looks like a firework type fuse.
These function by not spitting any fire out the side so that the shell doesn't get lit prematurely.
That's
so
smart.
you should only see it spit out the end once it's made its all the way through.
What's containing it? Like, what kind of material is containing it?
Well, there's a number, there's weaves of fibers in there and a layer of asphalt that really provides that waterproofing.
So you can kind of see how the signal is progressing. You can see how the fire is progressing through there. So obviously it's getting hot. Some of the gaseous products are coming up. Oh, is it gonna come out? Was that it?
That was it.
That is all that is needed to ignite the core of a firework.
So after that time fuse hits its end, it'll light a piece of black match that'll then flash into the burst charge. So that's what's represented by this blue material, which is typically rice hulls or something similar to that, coated with black powder.
What are rice? Oh, rice hulls.
Yes, rice hulls, not holes, sorry.
I was like, they're making rice holes, like donut holes.
The reason we coat rice hulls is because you get a very granular powder in the center of the shell now, which allows the flame to propagate very quickly through the shell, igniting everything simultaneously, creating that significant overpressure very quickly to blow the shell open. So a traditional peony shell would be your most basic of fireworks, where these stars would literally be lining the hemisphere, and then you'd have your burst in the middle. And that would give you a very symmetrical round sphere in the sky, your traditional firework that you see.
But it's just interesting to think that when you see a firework go off, you know, all those little points of light are about that size.
Yeah.
But they look, I mean, I would say that they look bigger, right? Because they're so bright, I guess.
Yeah.
So fast.
How fast does this thing go?
Pretty quick, and it is definitely trickier when it's dark like this.
Okay, can you see anything?
Once I go start looking here, I'm not sure.
How do you get focused to something that's not there yet, and you're not quite sure where it is or where anything is because it's all pitch black?
Because I basically have locked the exposure on this. We can at least see how the exposure is. Taking off?
Yes. Amazing. Blue.
Oh, shoot.
Okay,
Oh,
FPV is
dang.
down.
Oh, dang. I didn't realize I was so close to the ground. All right, hold on.
I just want to see what this looks like, you know. I want to check this out, so. Whoa, that is cool. I dig that.
These stars are made of black powder mixed with chemicals to give them different properties.
So brocade crown star would be the big bushy gold tail that you would see in the sky. So imagine a big glittering gold shell.
I could actually see the little pieces coming off and glowing pretty bright.
Now imagine those leaving a tail as they fly through the sky. It's a really spectacular effect.
This is gonna be blue.
Often the chemicals mixed into the stars are used to create specific colors.
Each of these stars would be coated with a primer composition, which is just a really fine black powder. The reason for that is a lot of color compositions take more heat to ignite, so they have a higher ignition temperature. So by coating with black powder with that primer, you're ensuring ignition of all the stars, which then transfer the fire to that color composition.
And then it started taking off on you? That's cool. I like that.
Jesus, bright.
The colors of fireworks are actually thanks to quantum mechanics. An element absorbs energy from the combustion, raising an electron to a higher energy level. And there are only certain transitions which are allowed, so when the electron drops back down to a lower energy level, it gives off light with the specific energy of that transition, which corresponds to a particular color. Some elements are particularly well suited to create certain colors.
So as the copper ions go in there, they absorb energy from the fire, from the combustion, and then the electrons drop back down to a lower energy level and they give out that blue light predominantly, and that's why we get such a great blue color. What a thing of beauty.
This is just a little interjection because I was looking at our flame tests, and the copper salt tests, you know, anywhere you look, copper fireworks are meant to be blue, like bright blue, but those flame tests look kind of green. And so I didn't really know what was going on, but I was sitting here playing with my kids with the KiwiCo flame test kit. I know, like, they did sponsor this video, but didn't tell me to put a section like this in. But what I found is that, okay, I'm using a copper salt here, and it starts out green, and then if you leave it for a while, come zoom in here, it starts to get blue. Oh, look at that blue. To get the beautiful blue color, I think you need more heat. I think it's a higher temperature that we need that we didn't achieve in our flame tests out in the field.
Here we got some calcium chloride. Oh yeah. Oh, that is a beautiful orange. Look at that. Here we're getting some potassium chloride to give us some violet. I'm not seeing too much violet, but maybe just a little. Barium chloride.
Of course, that's just small scale. Our pyrotechnician mixed up some color salt and fuel in a mortar.
What's in there is about 2 gallons of methanol with boric acid on this one. And copper 2 chloride on this one.
3, 2, 1, fire!
Yeah! That was awesome.
That is the beauty of quantum mechanics. The electron transitions that give rise to the color of fireworks are, at least in my opinion, way cooler than colored smoke bombs.
So the combustion products here are solid. That's why they make so much smoke.
In this case, there's just dye in the smoke to give it its color.
Yes.
To make so-called ghost shells, the stars are coated in layers of different chemicals, which allows them to change color mid-flight.
So assuming your shell construction was very uniform, your casing, all your stars are the same mass, you're going to get a very uniform explosion in the sky. So it's really as simple as how you lay out the stars in the shell, and it'll break in that pattern in the sky.
So what's your favorite patterned?
Jellyfish are pretty neat. If you've ever seen a jellyfish, it really looks like a jellyfish. You get the dome and then you get tentacles coming out the bottom.
That sounds amazing.
Yeah.
Do they just do it by changing the color and position of the stars up here? Like, how do you get a dome and then tentacles?
If this was the shell and you'd have another half this way, only the top half would be
fully
covered, and that would be your dome, and then you'd have a couple larger stars to create the large tentacles that come out the bottom.
These days, fireworks aren't usually triggered by lighting a fuse by hand, but by pushing a button.
Each one of these buttons would correspond to an individual firing circuit going out into the field.
The button sends current down the wire to an electric match. A little filament in the match heats up, triggering a chemical reaction,
which then spits fire into whatever you're trying to light.
Yeah, I think it's just,
Dust in the motors.
I think so. This might be a pretty quick repair.
We are about to have a fireworks finale in the middle of nowhere, in the pitch dark, for like a minute. And we're gonna try to fly FPV drone through it. So what does it actually look like to be in the middle where all the fireworks are exploding? In 3, 2, 1.
Thank you.
Can we get some light on the ground here?
That was insane.
The fireworks finale triggered my car alarm.
There were like 2 times where I was like, I'm not sure if I'm upside down or not, but I gotta hold this shot. Okay, so we have Gnare here.
Whoa.
God, that's...
Oh man, right through them, right around them. This part right down into that. Whoa! That is so weird.
Dude!
Oh.
Yeah! There we go.
You're upside down.
Yeah, right there. I was like, I got too excited. I was just chasing everything.
Crap.
Fireworks are this perfect combination of chemistry, light, and sound. If their purpose is to banish bad spirits, I'd say they achieve it. Hey, this video was sponsored by KiwiCo. You know, every time a KiwiCo crate shows up at our house, my kids get really excited. What is it, guys?
I love this one.
You light it on fire and it makes different color flames.
The different chemicals you put on?
Uh-huh. And that's because they know what's inside is a hands-on project that they get to build with me. And the building is a lot of fun, and playing with it afterwards is even better. From my perspective, the best part is that my kids are learning about science, technology, engineering, and design while playing and having fun, and I think that is the best way to learn. So the way it works is that each month KiwiCo delivers a crate right to your door, and inside is everything you need to complete the project, and I mean everything, so there are no additional trips to the store. We've been getting crates for 3 years now, so we've built lots of different projects, and they are all high quality. I got to tour KiwiCo's headquarters, so I saw how their crates are designed by experts and then tested with kids before they're ever sent out. They are also really good value. Most KiwiCo subscriptions work out to around $20 per month. They have 9 different product lines targeted at different age groups, everything from newborns up to 14 plus. So your kids can grow with KiwiCo just as mine have. I think my favorite thing is that working on these projects has become something that we do together. Every month there is this thought starter and an invitation to spend some quality time together, and it just arrives on our doorstep, and I really appreciate that. So if you want to try it out, go to kiwico.com/Veritasium to get your first month free. Using my link, you're not only getting a great deal, you're also helping to support this channel. And if you want to purchase single crates, that's also an option through the KiwiCo store. They make great gifts. So I want to thank KiwiCo for sponsoring this video, and I want to thank you for watching.